Hi, welcome to the SolidCAM 2021 Virtual Summit. My name is Amod Onkar and I'm the product manager for 3-axis and 5-axis milling. And today's session is about power of 3D milling in SolidCAM 2021. Let's get started. So the agenda for today's session is the following three points. The first one is we're going to see the 3-axis offering in SolidCAM 2021. And then we'll have a live demo of all the 3-axis functionalities in SolidCAM 2021. And finally, we will summarize the power and the features of SolidCAM's 3D offering in 2021. So what are we currently having in SolidCAM 2021 as far as 3D milling is concerned? We have HSR, which is 3-axis roughing, the generic roughing. And then we have 3-axis HSM, which is the generic high-speed machining functionality in SolidCAM. And then we have the new generation Turbo HSR and HSM, which is basically the new generation roughing and finishing operations in 3-axis. We also have iMachining 3D, the revolutionary product inside SolidCAM that allows you to machine parts much faster, about 70% more than the conventional way of cutting. And then finally, we have got high-speed surfacing for super finishing and machining localized area without the need to define any boundaries or stuff like that. So this is the current offering that we have in SolidCAM 2021 as far as 3D milling is concerned. Let's look at iMachining 3D. iMachining 3D is a revolutionary product inside SolidCAM 2021. It can save up to 70% machining time, even reaching up to 90% savings when you're machining with hard materials and small tools, both for 3D surface, that is the sculptured surface parts, as well as the prismatic parts. We use the optimized machining for each Z step using the proven iMachining 2D technology. And then we do the deep roughing using the complete flute length of the tool, shortening the cycle time and increasing the tool life. This is already demonstrated in iMachining 2D. We are using the same functionality in iMachining 3D. And then we remove the scallops or the rest material in small upward steps optimized for constant scallop height, and it further shortens the cycle time for machining any kind of 3D part, whether it is a sculptured surface or it's a prismatic part. We also do intelligent localized machining and optimal ordering that eliminates almost all long position moves and retracts, which means that we do scallop removals not on the entire part but based on where they are located, and we also do long positional moves. That means we don't retract to the plane every time when we have to move from point A to point B. If there are two extreme ends of the part, we just connect them from outside the part on the same plane. The stock is updated dynamically, and at every given point in iMachining 3D, we always use the dynamic 3D stock, which is available to SolidCAM at every given point. And the toolpath automatically adjusts to avoid the contact between the tool, the holder, and the updated stock. So if the updated stock or the holder comes in close contact with the updated stock, the holder and the tool assembly is pushed away from the updated stock by the value defined by the user as a safety value, thereby avoiding any kind of collisions with the holder and the updated stock. Remember, we talk about updated stock and not just about the machined part, okay? Not the final part. We are also taking into account the updated stock. And the whole thing, the combination of iMachining 3D, HSM, HSS, and Turbo HSR can be used to complete any given part today in SolidCAM, whether it is a small, medium, or large part. Everything can be done within the ambit of SolidCAM's 3D offering. Let's look quickly at a short demo of iMachining 3D. I have a part already defined here. So what you need in iMachining 3D, like you might have seen in iMachining 2D, is we need to define the machine, the material, the machining level. So in this case, I have defined a AMS MCV 450 machine with a maximum RPM of 8,000, a feed rate of 10,000, and a spindle power max of 11 kilowatt, the continuous spindle power, and an efficiency of 95%, which basically says that it's a direct driven spindle. And as far as the material goes, we have defined an impacts bowler. This is a tool steel from Bowler, and it has got an ultimate tensile strength of 1020 megapascals. So I'm going to save and exit this. And I've set the machining level as 6. We'll quickly come to that. Let me edit the tool path. So I've got the first tool path. I will edit my machining tool path. In the geometry, I've got the target, so the entire target can be selected. You don't need to define any 2D boundaries or anything like that. In the tool, I have got a 16 diameter. It's a 16 corner radius 2 bullnose tool. Okay, now I'm going to just remove this holder, and we go to the new tool table. We have got this option to add the adapter, so I'm going to use a BT40 adapter here, and I'll also use a BT40 shank. So this is how the tool is going to look like. Okay, so accept that, and let's go to the levels. You can see that the software SolidCAM has already picked up automatically the user upper level and lower levels. Technology wizard. Here I'm going to define a machining level of 6, and you see that it has taken 3 depth of cuts of 31 millimeters each. How has it arrived at 31 millimeters? It's pretty straightforward here. It looks at what is the cutting length available to it. So the cutting length available here is 35 millimeters. So anything within the ambit from 0 to 35 is what it is going to find out the best possible cutting length in order to maintain the ACP within a close range of a whole number. So it's given me a depth of cut of 31.03, and the RPM is calculated, the feed rate is also calculated, step over max min is calculated, which generates a VC of 313 and a chip thickness of 0.18. And we have got the power requirement here at 6.5 kilowatt, and that's basically because I'm using the turbo mode. If I don't use the turbo mode here, you will see that the power requirement drops down to just 1.2. We are actually underperforming on this spindle, which has 11 kilowatt spindle. So I'm going to use the turbo. It's going to generate about 6.5. That's roughly about 60% of the spindle power. We can easily touch 70%, but we are not going to do that. We are going to use a 60% spindle power. And in the technology, I have got a wall offset of 0.5 and a floor offset of 0.5. Scallop, I've kept it at 1. I've done the overriding. If I remove it, it comes to 2.64. I don't want such a high scallop. I would like to keep a scallop of 1 millimeter here. So I'm going to save it, and let's calculate the operation. iMachining 3D utilizes complete it's a 64-bit calculating engine, so you can see that it is utilizing all the cores available on the system for calculation. Therefore, calculation speed dramatically goes up if your number of cores are higher. So I have got the toolpath here, and if I run the simulation now inside SolidCAM's new simulator, this is how my part looks like. And that's the tool loaded on the vise, and we can start machining it. And that's the simulation. That's how it's going to do. It takes the complete depth of cut in one go, and then it does the scallop removal by going in the upward direction. Right. So this is how iMachining does the roughing, and the total time here is 8 minutes 48 seconds for cutting this part on an impacts boiler with a tensile strength of 1020 megapascals. Right, let's jump back to our presentation here and let's move ahead. Let's move to generic HSM, which is our oldest 3-axis machining engine that's been with SolidCAM from a long time. It's a time-tested 3-axis machining engine. Been more than 10 to 12 years now that SolidCAM has HSM inside its kitty. We have got complete control over all the parameters of machining, whether it's roughing, rest roughing, or finishing. Everything can be controlled totally. Toolpath editing functions. You can edit the toolpath after they have been calculated using boundaries, Z levels, or combination of boundaries and Z levels. The toolpaths are smooth and the links are even more smoother. We have comprehensive set of boundary creation tools, which you are going to see in that short demo that I'll perform after we finish this. And we have got 5 roughing options. You can rough the part the way you like it, and about 20 different finishing options, which means that you could finish the part the way you want. There are no restrictions. You can machine the part the way you think the part needs to be machined. So if I look at the gist of the HSR and HSM, we have got powerful roughing and the finest finishing toolpaths available for 3D high-speed machining of complex parts and aerospace parts, molds, and dies. We have got unique machining linking strategies for generating high-speed toolpaths. Cutting moves and retracts are smoothed to maintain continuous machine motion. Retracts are kept down to minimum to minimize air cutting. And the toolpaths are smooth and efficient, which translate to very high surface quality. So this is the gist of the HSR. Along with the HSR functionalities, in 2021 we introduced something called as a geodesic machining, which uses the power of consistent or constant step over using different formats of machining or different patterns of machining. We have got 2 patterns of machining, and this can be performed on a group of surface or over the entire solid model. It could be morphed between 2 curves, or the pattern could flow parallel to a given set of curves. So SolidCAM's geodesic machining uses a global distance field without any fixed direction as a reference for calculation. I'm going to explain to you what exactly this means, which enables full flexibility of calculating various pattern types while maintaining constant distances or constant step over between cuts. So when we say that it uses a global distance field without a fixed direction as a reference, generally in 3-axis, when step overs are being calculated, they're always calculated from the direction of machining, which is in case the Z direction. So in geodesic machining, we do not look from the Z direction when you are machining the surfaces. Instead, we look normal to the surface. Each surface that is being cut, we look normal to that surface and calculate the step over. If you look from the top, you will feel that the toolpath is quite crowded in a certain area, but when you look normal to those surfaces, you'll realize that the toolpath was actually having consistent step over that particular surface. So we do not look from the Z direction, but we look at the direction normal to the surface that's being machined. Let's look at a very quick demo of the functionalities in HSR and HSM. Right, so we have done the 3D iMachining. We can suppress this, and instead of using a 3D iMachining, what I'm going to do is I'm actually going to use the 3D HSR functionality to do the roughing of the same part. So I'm going to use contour roughing. So like I said, there are 5 different roughing options in HSR. So I'm going to use contour roughing. The tool that I'm going to use is T1, which is a 16 bullnose. And in the constraint boundaries, I'm going to create it automatically. In the passes, the step down, I'll set it to 1 millimeter, refine the corners, and none in adaptive step down. Link, I'm going to use a climb machining, and a ramp angle of 5 degrees and a height offset of 2 millimeters, and the retract minimum vertical retract. You can see that the number of parameters also that are needed to be defined in HSR is pretty bare minimum. And let's hit the calculate button. Okay, that's the calculation. So this is how the calculation looks like, or calculated toolpath looks like. Let's run the simulation pretty quickly, and let's go into Solid Verify this time. So let's run the simulation. That's it. Okay, so my roughing is done. I'll now go over to rest roughing of HSR, and the tool here I'm going to use is a 10 diameter ball nose, and in the constraint boundaries I'm going to use an automatically created constraint boundary, and my all parameters are mostly going to remain the same as they were with the earlier toolpath. Save it, and let's hit the calculate button again. Okay, now what you can see is it's done pretty decent machining, but there are certain areas where I really don't like that machining is happening. For example, on this region here, this is happening because it's finding scallops on this region, and I don't want it to go into these regions to do any kind of machining. There are two ways of fixing this. The first way is I can use toolpath editing functionality in HSR and HSM and remove the unwanted passes. The other one is to reorder the operations in such a way that I do not get the cuts outside a certain area. In order to do that, we need to understand that I have got another operation here, which is a geodesic machining. And in geodesic machining, if I edit it, you can see that we have got a geometry here where I've selected the faces, all these faces, the blue colored, purple colored faces, and I'm going morph between two curves, and the surface boundaries are detected automatically by SolidCAM. I'm using a tool of diameter 12, and how the toolpath looks like is here. This is a very nice looking toolpath that it has generated, and we are using consistent or constant step over. But in this case, when I'm using a morph between two curves, the constant step over principle is overridden by what we call as the maximum step over. So I have defined the maximum step over here. So there are regions where the step over can actually be lower than the maximum step over. Okay, that's because of the pattern generation type that we have used, which is the morph between two curves. So I'm going to reorder the operation. I'm going to move the geodesic machining right after roughing. So I'm going to move it right after roughing, and you can see that my rest roughing now becomes uncalculated, or it gets the motions gets deleted. So I will just hit the calculate button here. You can see the stock now gets recalculated, and my rest roughing operation starts getting calculated again. You can see that I now no longer have any any motions outside this region. I only have motions inside. Now let's look at why the depth of cut was so less. So let's go to the passes. The step down was 1 millimeter. I'm going to change it to 0.3, and we will just hit the calculate button again. Okay, looks much better. We have got machining happening in all those regions where there is material remaining. So that's about rest roughing. The next thing that we did was to use constant Z machining, and here I used the slope angle principle and asked the software, or asked HSM to machine using constant Z from 47 degrees to 90 degrees. So like I said, there are 20 different machining options in finishing. So you can choose to machine the way you like in SolidCAM's 3D HSM. There are several options, right from constant Z machining, helical machining, constant 3D constant step over, pencil milling, corner offset, morph machining, spiral machining, linear machining. You can choose the way you would like to machining. So I've used the constant Z machining with a slope angle from 47 to 90, and this is how the toolpath looks like. The remaining areas I'm used linear machining to go from 0 to 48 degrees, and this is how the machining looks like. Now for me, I did not like that it entered into this region here. So SolidCAM allows you to edit toolpaths even after they are calculated. So we can run the edit HSR and HSM toolpath, and this time I'm going to use the boundaries. And in the boundary, let's look at the boundary. That's not the boundary that I'm going to use. We have got several ways of defining boundaries, but I already have the boundaries in this case. So I'm going to use the boundary that has been already predefined. So I'm going to use contour 3. You can see these are the pink colored boundaries that I'm going to use. And I'll say keep the toolpaths outside the boundary, and let's run the calculation. Okay, it's just running the relinking. And that's it. You can see that the toolpath was trimmed out from that region completely. So the original operation is suppressed. So in case you have done some mistake, SolidCAM will allow you to go back and recorrect and re-edit the toolpath. Okay, so the original operation doesn't get deleted in SolidCAM. And then we have those two regions, and those regions here machined with 3D constant step over toolpath. Again, a very efficient way of machining regions like this, where you would like the tool to follow the profile of the area that you are trying to machine. And then we can do the rest machining. Again, you can see that rest machining has gone into this areas. We can still use the regular toolpath editing and just remove these regions from our rest machining. And in rest machining, it does it completely in a very intelligent way. The steep regions it automatically detects, and it does with constant Z, and the shallow regions it will run the tool along the profile. And then when everything is performed, we can machine the region that was trimmed out in rest machining using the constant step over machining toolpath pattern. So this is about the HSM and HSR functionalities in SolidCAM. And like I said, you could machine any kind of part with it the way you want. A lot of roughing options, tons of finishing options available. Toolpath editing is available, so you can finish the way the toolpath, finish the part the way you would like to machine. Let's go ahead. Let's go to the next topic in our presentation, and that's about the new generation turbo HSR and HSM. It's a new generation 3-axis engine. It's extremely fast in toolpath calculations, lightning fast in tool recalculations of the toolpath, true 64-bit architecture utilizing all the cores for toolpath calculation. If you have 8 cores, and if you have a 12 core, and if you have a 16 core machine, you can imagine the speed of calculation. It will start increasing dramatically as the number of cores on your machine increase. Minimum definition of parameters, especially in turbo HSM, allows users to learn the product very quickly and get productive within a day. For roughing, we have got contour, hatch, and rest roughing patterns, and there are finishing patterns available which are constant Z, linear, constant step over, including rest machining for finishing. And a complete collision control with a holder is available in Turbo HSM. So if we look at the functionalities of turbo roughing or turbo HSM, we have got a multi-core support. It's a true 64-bit calculation engine. Speed of calculation increases as the number of cores increase. Faster recalculation because we store the parameters like a parametric product and we just change the values and the recalculation is almost instant. We also have got a feature where we can offer users multiple surface offset. You could create groups of surfaces and provide different surface offsets to those groups. Infinite groups of surfaces can be created by the software. In the strategies, we have got both hatch as well as contour machining, and then we have the rest roughing option where we provide a complete stock-based rest machining, or it could be based on the previous tool, but you can also have a combination of stock as well as the previous tool when you're doing the calculation. Users can also specify minimum stock thickness above which the toolpath will not be generated or will be generated. Arc fitting is possible in rapid motions and provides smooth transition between passes, so the movements on the machines are also going to be much smoother. And arc fitting is also possible inside the toolpath, which reduces the toolpath length and improves the machining quality on the machine, especially on the older generation machines where a lot of points are very difficult to process by the controller and the machine sometimes gets slow or starts jerking when only points are sent for machining. So the arc fitting helps these kind of toolpaths to be taken even on a very old machine and machine the part efficiently there. As far as finishing goes, we have got constant Z in Turbo HSM. So it has got adaptive step down as well as flat area detection. Zigzag, one-way and spiral strategies are also available. Then we have the linear machining and with constant step over, scallop as well as the adaptive step over. We also have optimal machining angle that we can that the software can decide based on the XY plane and based on the XY plane based on the part geometry. So you can see here in this particular example where we have used the linear machining with an optimum angle, you can see that the toolpath is not having the same pattern everywhere. So you have one pattern going in this direction. For another region, you have got the pattern going in that direction, and for the third region, you have got the pattern going in a different region. This direction of the pattern is automatically defined by SolidCAM. And this reduces the machining time because what SolidCAM does is it tries to make the pattern to reduce the acceleration and deceleration patterns on the machine. It tries to limit it. And then we have the 3D constant step over based on the scallop or the 3D constant step over. We have 5 different cut ordering methods, and the leads and links are automatically applied. Let's look at a demo of Turbo 3D HSR. So I'm going to open a part. And this is a fairly large part, we can say. Not very large, but comes in the medium to large category. So here I've machined using several options available inside SolidCAM 3D. The first one is I've used what we call as the Turbo HSR. I have used a tool here of 32R 1.9. This is a high feed tool, a bullnose tool, and the depth of cut here is 1.2 millimeters. And the step over here is 40% of the flat region of the tool, of the bullnose, not the diameter, but the flat region of the bullnose, which comes to about 11.28 millimeters. So we have the ability to define the start point, and it's a one-way machining. So let's look at how the toolpath looks like in simulation. So I'm going to go into the SolidCAM simulator. And let's run the simulation. it's a very conventional way of cutting, but the calculation and the parameter definitions are pretty much easy and they are pretty quick. The calculation is pretty quick. And this is how the roughed out part using Turbo HSR looks like. Okay. After that, I used a diameter 16R1.9, which is also a high feed bullnose, and I used the previous stock here. So I've asked Turbo HSR basically to respect the stock models and detect material more than 0.8. Remember, in my previous operation, I have kept a stock of 0.7, so I'm slightly increasing the stock with the tolerance that I use, that is 0.1, and I tell to SolidCAM that it should detect material more than 0.8 millimeters, and it should only machine in those regions where the stock is more than 0.8. And this is how my toolpath looks like in the simulator. So what I'm doing now, again in SolidCAM simulator, it's loading the roughed out part, and this is how my rest roughing looks like. You can see that it's only going into regions where material is remaining or material is more than 0.8 millimeters. It is not going into every region and trying to machine every scallop possible on the part, but it's only going into those regions where the stock was remaining. So that's how it's done. And then I have done another rest rough with 10R1. Let's run the simulation. Again, this is using the turbo rough principle. So this is how the stock was remaining before. Let's run the simulation. Again, you can see that it's cutting only those regions where material is remaining. Very, very efficient rest roughing. Bare minimum retracts, keeping the machining very, very efficient and smooth. Right. After this, I also did what we call as a corner rest finishing using the Turbo HSM functionality, which is called as constant Z rest finish. So it uses the principle of constant Z, but it does what we call as a rest finish. And you can see that it's only going into the regions where I've specified my previous tool and the new tool, and it tries to find the regions and goes only in those regions to machine the areas in constant Z. After that, I've done horizontal areas machining using HSM's horizontal machining principle or horizontal machining toolpath. This is how the toolpath looks like. It's ramped and it's only detecting and machining regions that are absolutely parallel to the XY plane, so which have got absolutely 0-degree slope. And then we use the new generation functionality of geodesic machining to machine some regions which we feel are suitable to geodesic machining. You can see that it's running with constant step over. Even though this is a vertical area, it's looking normal to the vertical area and generating the step over. So it is not looking from the Z direction to generate the step over, but actually looks normal to the surface here and generates the step over. So I've done the machining so that it starts at one point and it's like a spiral toolpath. It keeps winding around the part till it comes to the end. And then of course we use the constant Z functionality and machine those regions where we do not where the slope angle is between 45 degrees to 90. And then I also machine the locks here using constant Z. This is using the Turbo HSM. And then the remaining regions are machined using the linear machining principle. Again, here we are going between 0 degrees and 47 degrees. It's not exactly 0, but if you see that we are used, if I edit this toolpath, we are doing it with 0.01 because I do not want SolidCAM to again machine those regions which I have already done with horizontal machining. Horizontal machining is 0, so I said slightly more than 0, 0.01 to 47. So it leaves out all these regions where horizontal area has already finished it. Okay, and then the parting surfaces, we have machined it using, again, linear machining, turbo linear machining with 10 ball mills and some rest machining. You can see how nice and smooth the tool paths are using HSM's rest machining. So I have used a combination here. Majority of that is being generated by turbo machining technologies, while in between certain regions I'm using the HSM tool paths also. I'm running finally with the pencil machining functionality in turbo machining. We've got the pencil machining functionality, and that just goes around all the corners. And then we have got the HSS machining principle, which is basically the surfacing function, which we will see a slide later, where I have done the top fillet finishing. You can see how smooth the tool path is. It starts from one and ends at the other one. So it's machined the entire fillet very smoothly with a ball nose tool. So I've used the HSS principle here. If you look at what we have used inside HSS, it's basically parallel to curves, and I've selected this geometry here, these three surfaces, and they go parallel to this curve, the top curve. So once I've defined that, the tool path comes out very smooth. So I've done the lock machining or the lock top machining of both these regions using HSS, which is the high-speed surfacing functionality in SolidCAM, where you can machine localized surfaces without the need of defining any boundaries. Just pick the surface and SolidCAM will machine them by the pattern that you want. Right, let's get back to our presentation, and we will quickly recap HSS, which we saw as the lock machining that I just showed you. It's an excellent complementary module for high-speed surface machining of localized surfaces. Advanced collision control for holder, arbor, and tools. It supports both standard as well as shape tools, which means you can have machining done even with using dovetail kind of tools. It can machine undercuts. It doesn't need any special functionality. It can handle undercuts straight away inside HSS. And it's a very important module for every shop, because there are certain regions in every part where you do not want to use the full 3D power of machining certain areas. For example, certain fillets you need to machine, you can use HSS there. So it's a very important module for every machine shop. And then we come to 3D undercut machining. This was again recently introduced inside SolidCAM. We can machine any part now using constant Z, and even if it has undercuts, it doesn't matter. You can machine the parts completely using a constant Z principle. So it works directly on the models, constant Z strategy. It supports slot mills and lollipop cutters, creates absolute collision-free tool paths both for the cutting area as well as the arbor and the holder. So it has got automatic collision control for shank and holders. Let's look at few test cases that have been machined, or the parts that have been machined using a combination of iMachining 3D, turbo roughing, turbo finishing, HSR, and HSM. The first one is basically a die mold part, a P20 steel done on a Makino PS105, and you can look at the surface quality that was achieved. This is right after machining. No hand finishing was done for this part. Machining time 240 minutes. The size of the part is 200 by 160 by 40. The same part was done on an Indian machine, Jyoti VMC 850. Die mold part again, P20 steel. 300 minutes was the cutting time, and this is the part coming out of the machine as it is. Another part that was done using iMachining 3D, HSM, and HSS, also on Jyoti VMC 850, a die mold part on P20 steel. This was done with 200 minutes. This was a machine with Siemens control. And finally, this large part, the part that you saw at the end, was completely machined as it is with the functionalities that were shown to you in the part. on an AMS MCV 450 P20 steel, and the entire part was done in about 400 minutes. So if you have to summarize now, we have got a very powerful milling, 3-axis milling solution now in SolidCAM 2021. You can rough and finish any part of any size with ease. A combination of complete control and automated definition of parameters are also available inside SolidCAM 2021 3-axis machining. We have toolpath editing functions, true 64 machining engine, automatic leads and links, local area surface machining using HSS for super finishing, machining of undercuts, and geodesic machining provides constant step-over machining for any kind of surface. Adaptive feed rates automatically adjust the feed rate in tight areas, very important when you're using inserted kind of tools. Arc fitting with a given tolerance, they've reduced the G-code size by almost over 60%. Well, that was it. That was the power of our 3-axis machining inside SolidCAM 2021. Thank you very much for watching this video, and we wish to communicate to you again in the near future. Thank you once again. Bye-bye.